good. It looks good. Okay. My audio should be right, I think. Okay. Let's go ahead and begin. Okay. In today's video, we'll be looking at a sort of an evolved problem involving the solution that we had from homework B. So when we looked at homework B, we looked at a cylinder that was in steady state that had no heat generation and only had heat flow in the radial direction, so D of R, right? Now what we're going to do is we're going to take that derived equation that we solved for. I'm just trying to underline to state a point. We're going to take this equation and specifically extract the resistance of it to show the overall thermal resistance of this same pipe put in a layer or another radius of insulator to then observe what the critical value of this insulator is to determine how much insulator we need to actually uh, get something of value from this. Because if we determine that it's a minimum, for example, if we put too little, it'll actually have the inverse effect that it's intended for, which is to keep heat in. So let's go ahead and I'll start by explaining what this diagram is, just so that we're all on the same wavelength here. So we have this pipe that's in surrounded by a layer of insulator with the length of it, I'm just gonna call it L in this case. We have our first radius. Uh Actually, yes, these are supposed to be connected. We have our first radius, which is just kind of showing our inner radius of the pipe, or just the radius of the pipe itself. And then we have R2, which is the total it is the total length of both the insulator and the pipe together as the radius. So, what is it? If we want to find the overall thermal resistance of this, we have to consider the heat transfers being done here. So, when we solved for the thermal resistance of the pipe, we said that there was a thermal conductivity event, meaning that it is heat transfer via conduction. This is different when we use an insulator in this case that's exposed to outside air. Because of the situation that it's in, we actually say that it is heat transfer via convection instead. And so we actually have to approach this a little different. Um, First off, we need to actually extract the heat convection equation. So I'm going to say that Q equals our heat convection constant times area multiplied by our change of temperature, which if we're going to put this in the same terms and extract resistance from this, we're going to say it's change of temperature, which equals our heat flow multiplied by 1 over HA, which look at that, we have our resistance. So to get our total resistance, we would say R total equals R conduction plus are convection because these two are in series with each other. It goes from the pipe to the insulator. It's congruent and it's the same series as if it was a, a resistance of voltage that's in series with each other. We're going to add them because of that. So let's go ahead and kind of translate this resistance to more of the language of the equation that we solved earlier. So we know that the area in this case is just going to be 2 pi L multiplied by R2, right? So, oh, and I should also note really quick, this isn't inner and outer the way that we made it last time. This is R1 and R2 in this case. That's the only change I made to the previous equation, just to kind of put it in terms of this pipe problem. It's essentially inner and outer, but now it's in relation to insulator now. So that's the change I made there. But that's the only one that I made. So now we have an area for this as well as the uh as well as our convection coefficient that we have. So if we want to go ahead and make the R total expression, we can say that R total equals natural log of R2 over R1 over K times 2 pi L plus, and this is 1 over H multiplied by 2 pi L R2, right? So what we need to do is we're going to take this to the first derivative and set it equal to zero. Why is that? That seems pretty random, right? Well, the reason why is because we are trying to find the extrema of this equation. We're trying to find when the first derivative equals zero such that we can find a maximum or a minimum. Because depending on that answer, we are going to approach this problem very differently. So, let's go ahead and set the first derivative. So what are we going to set this in regards to? We're going to set the resistance total to the derivative of R2 because we want to find it for the entire system. So if we do that, we get natural log R2 R1, which should look like R1 R2 multiplied by 1 over R1. Make sure my math is right. Yes, that is the derivative of that. Then we do that over k multiplied by 2 pi L. Now we're going to add this to 1 over, in this case, actually no. This turns into a negative because it's R2. This would turn into negative 1 over R2 squared. Yeah. So it's to be minus 1 over H 2 pi L R squared. Okay. And this is equal to 0. So something we can do is we can remove R1 from this side, and we get 1 over R2, and we can go ahead and remove 2 pi L because this is set equal to 0, and then we get 1 over pi, we get 1 over R2 times K minus 1 over, and this would be HR squared, which equals 0. I'm making sure I'm not missing any constants. Cool. Okay. So now what we can say is let's go ahead and shift this over. So we have 1 over R, 1 over the second radius times the thermal conductivity constant, which equals 1 over the thermal heat convection coefficient, R squared. And now we can multiply, let's see here. I'm going to flip reciprocal. And now all we need to do is divide by HR. And this should give us K over H equals R2. So now we have this critical value. Let's see here. Yeah, so we have this critical value now. So we want to say that we what we want to do now is we're gonna take this value and to get a maximum or a minimum of an equation, what you want to do is take it to the second derivative and then apply that extrema, and now we're gonna see if it is a positive or a negative value. So let's go ahead. We have dr total. Just to kind of keep track, this is our first derivative, or d of r2 equals, let's see here, this equals 1 over r2k minus 1 over h r2 squared. So now we're going to go ahead and set it to the second derivative, total over d of r2 squared. And when we do this, we get, this would be negative R squared, and then this would be plus 2 over, this would be cubed. And so when we do this, wait, do I have my right variables? Okay, I should. Yes. Yeah, we do. Okay, so when I do this, I'm going to sub in R of 2 equals K over H. And when I do that, I'm going to get 1 over K over H squared multiplied by R2 squared plus, or wait, KH squared multiplied by K squared plus 2 over H multiplied H cubed multiplied by K over H cubed. Now, when I simplify this, it's negative. We'll get something that looks like K squared over H squared multiplied by K squared over 1 plus 2 H cubed multiplied by K cubed multiplied by H cubed. Believe I may have done something wrong. Did I do something wrong? That side looks more right. Pause the recording really quick. All right, sorry about that. I led us down a wrong path because algebra is not my strong suit. We're gonna go ahead and redo this. So this is gonna be KH2 multiplied by K. It's gonna be plus K over H cubed times H. H and K are not in parentheses there. I don't know why I expressed it like that. Um, all right, so let's go ahead and express this. We have squared over H squared multiplied by K, and over here we have K cubed or H cubed multiplied by H, which when we simplify this, this should give us negative 1 over, this would be K cubed over H squared plus 2 over K cubed over H squared. And when we add these two, we get 1 over K cubed over H squared, which this looks like a positive value. So what does that mean? Our second derivative, once we plugged in our extrema, came out with a positive value, meaning that we are looking at a minimum value here. So why is this a headache? Well, let's go ahead and sketch it, right? Let's visualize this. So we have our R total, and let's say that this is at R1, right? So at this point we have the thermal convection, which in this case is going to be 1 over HA, and this is, we're going to put this in 2 pi LR1 in this case. So if this is a minimum at the extrema value that we found, which is K over H, we know that starting from our initial resistance, Sorry. That, this is actually our minimum value. Let me write this with better handwriting. Minimum. So what that means is if we added as much as this critical value has, if the insulator was as thick as this right now currently, that is the minimum value of the total resistance that we could have. Meaning that if we added that much, we actually created a much worse problem. The insulator is doing the inverse of what it's supposed to do. So this is a very bad problem to have. So what we need to do is realize that it does go up. This is the minimum value, so it can go up. It can only go up from this point, meaning there comes a point where eventually we've intercepted our original thermal conduct. I mean, our th total thermal resistance, which happens to equal this value. Meaning, what we can say is, okay, if we're not targeting our minimum value, but instead we are targeting the value in which this finally reaches the previous or the initial total resistance, then that means we can set it equal to that and say that, okay, well, if we add this much insulation, then we can find a way to have a real value for our insulator to then say, okay, I need this much thickness, and anything beyond that is actually going to contribute and give us insulation for our pipe.